Hello and welcome to Nunley Math. I am your host, Aaron Nunley. Thank you so much for joining us once again as we talk about solving inequalities. We've already introduced the idea of an inequality, and we've talked a little bit about how to graph those or show those on a number line. But today we're going to take that a little further and talk about how we can solve larger inequalities or inequalities that require us to perform mathematical operations. Now, there's some ideas in here that I think are some of the more challenging ideas that we have in Algebra 1, and so I'm going to do my best to clarify those for you. If we can wrap our mind conceptually about what's going on, I think the actual practice of solving these is actually not too terribly difficult. So, without further ado, let's take a look here real quick. I want you to consider the inequality x is greater than 5. And I'd like us to graph several examples of x is greater than 5 on that number line. Hopefully you have a number line in front of you. If not, I'd suggest pausing the video and getting a number line out and trying to graph several examples because there's a point I'm trying to illustrate here. I'm going to go ahead and assume you've done that, and I'm going to start thinking about numbers that make that statement true. Remember, that's the definition of a solution, is anything that would make the statement true. Well, 6 is greater than 5, so I can plot that on the number line. 7 is also greater than 5, so that would be considered a solution as well. So would 8, so would 9, and so would 10. In fact, every number along this side of our number line would work. Now we know 5 is not greater than 5. 5 is not greater than 5, but I also know that 5.1 is, 5.2 is, 5 2/3 are. Everything in this little section between 5 and 6 is a solution, but the 5 itself is not. So I put an open circle there. Hopefully that was not too overly complex to understand. Notice the arrow goes on and on forever because anything on this side of the number line is going to make this a true statement. Notice the things that do not have the line will not make it a true statement. 4 is not greater than 5, 3 is not greater than 5, and so on and so forth. But I use this because I want to compare it to this problem down here. Negative x is less than negative 5. Negative x is less than negative 5. I would suggest pausing the video for just a second and trying to find solutions to that inequality as well. I'm going to go ahead and keep going with the assumption that you have already done that on your own. In trying to find values that make this true, notice that if I plug a 6 in for x, a 6 in for x. Notice the negative sign is already here, so I'm plugging in a 6. Negative 6 is less than negative 5. So I put that as a solution. If I plug a 7 in for x, I get negative 7 is less than negative 5. Also true. If I plug an 8 in for x, negative 8 is less than negative 5. Same thing happens with 9. Same thing happens with 10, and so on and so forth. In fact, you can see from the pattern that if I were to plug in an 11, it would also be true, 12, 13, 14, and so on and so forth. In fact, every value that's greater than 5 is going to work. Now, if I were to plug a 5 in, negative 5 would not be less than negative 5, so it would not work. Do you notice anything strange or unusual about these two problems? Hopefully you realized that they both have the same set of solutions, or the same solution set, as we would say in math. Now, to me, that is extremely, extremely odd, because this is looking for values that are greater. This is looking for values that are less than. Notice greater than, less than. It seems strange to me that they would have the exact same solution set. And really the reason for this confusion lies in the fact that this x has a negative sign attached to it. And a negative sign is going to do some really strange things to an inequality. That's what we're going to look at for the next several moments Once we get that idea down, the rest of this in practice is not overly complex. Let me give you another set of problems. Consider this. If you were to graph x is greater than or equal to 2, x is less than or equal to 2, and negative x is less than or equal to negative 2. We can begin to see some of the problems that arise with negative signs and inequalities. I'm going to go ahead and assume that you've done these on your own, or you can do them very quickly, and I'm going to do the first two fairly quickly. If I'm looking for all values that are larger than or equal to 2, well, that's going to look like this. 2 is equal to 2. 3 is greater than 2. 4 is greater than 2. 5 is greater than 2. We get all of these. Most of us, I think, are okay with that. If I'm looking for values that are less than or equal to 2, well, 2 is still equal to 2, but those values are going to be over here on the left side of the number line. Notice 1 is less than 2, 0 is less than 2, -1 is less than 2, and so on and so forth. But when we get down to this inequality with the negative signs, once again we have to be very, very careful. So I'm going to suggest again, if you've not already worked this one out on your own, you pause and look at these values one at a time, plot the points, and then use that to make your determination about what's going on in the problem. Assuming you've already done that, I'm going to go ahead and plug in some points myself. If x is a 3, I get -3 is less than or equal to -2, and that's a solution. If I plug in a 4, I get -4 is less than or equal to -2. That's also a solution. 5 does the same thing, as does 6, as does 7, and of course, -2, if I plug in a 2, -2 does in fact equal -2, even though I have a dropped sign there that I will have to go back and correct later on. Notice that one is true, so I would put a dot there as well. It's everything to the right of that -2. Once again, our first reaction is to think, wow, since this is a less than, it should be similar to this problem. But notice the solution sets are very different. These two are not the same. In fact, x is greater than or equal to 2 has the same solution set as -x is less than or equal to -2. They have the same solution set. In fact, if I were to take that second inequality, -x is less than or equal to -2, and I were to try to apply the properties we learned in our other units to this inequality. For example, knowing that I can multiply by a 1 at any given point in time is the identity property. Knowing that if this is multiplication, I can divide both sides by -1, notice what happens. I will get an x over on the left, I will get a 2 on the right. But in order for these to be the same, this sign has to switch. This is a very interesting characteristic of inequalities, that if we multiply or divide both sides by a negative sign, in order to maintain the truth of the inequality, we have to flip that inequality sign. Other than that one specific peculiarity of inequalities, these solve exactly the same way that equations solve. In fact, this is how we develop the property of inequality. I can do anything I want to an equation as long as I do it on both sides. That's the property of equality. However, if I multiply or divide both sides by a negative number, I must reverse the inequality symbol. Now I'm going to tell you that most math teachers are going to tell you to memorize that. Most math teachers are not going to go through and show you examples that illustrate how it works. And I'm going to go even one step farther than this, and I'm going to try and help you understand why this works. Most mathematicians have a hard time articulating this. I do not claim to be an expert on how to say this, but I am going to try and put it in some words that make sense to you. Because if we can remember why we have to flip that sign, we're going to be much less likely to forget to do it. So consider this. If I have 4 is greater than 2, what I'm really saying is that if I put 4 and 2 on the number line, 4 is going to be closer to the right, or further to the right. The farther to the right the number is, the greater the number. The farther to the left the number is, the less the number's value. Hopefully that's something you're already comfortable with. 4 is greater than 2 because 4 is further to the right on the number line. Now, I want you to think about this. If I were to multiply both sides of this inequality by 2, using the property of equality that we learned earlier on, we would expect for that 2 and that 4 to both get twice as large. 4 times 2 becomes 8, and 2 times 2 becomes 4. 8 is greater than 4, which is still true. Notice, if I were to plot those on my number line, the 2 times 2 becomes the 4, and instead of going 2 places to the right, it's gone 2 places and 2 places again. The 4, instead of just being, I'm going to switch colors here, I think, instead of just being 4 spaces to the right, is now 4 spaces to the right 2 times. You see, we wouldn't expect the truth of this inequality to change, because if 4 is farther to the right to begin with, we would assume if we double that, it's still further to the right. Let me say that again. If going 4 places is further to the right than going 2 places, then going 4 places twice is going to be further to the right than going 2 places twice. Now that's a little convoluted. If you're having trouble understanding that, you may want to go back and listen to it again, because it is just a little bit tricky, but it is very important for what we're going to do next. Because if I come over here and do the exact same thing, but instead of multiplying by a positive 2, I multiply by a negative 2, I get, there is, negative 8 is less than negative 4. Back that up. Think about this. If I were to multiply both sides by negative 2, instead of by the positive 2, look at what happens. 4 is further to the right than the 2. That's our original expression. When we did 4 times 2 and 2 times 2, we already said that we are further to the right with the 8 than we are the 4. Remember, going to the right 4 twice is more than going to the right 2 twice. But the negative sign does something interesting. When I use that negative sign, instead of going to the right, I actually end up going to the left. And I end up at negative 8 and negative 4. You see, this negative sign changes the direction of the problem. Instead of saying I go to the right 2 and 2 a second time, what I'm actually saying is I'm going backwards twice, backwards 2 twice, or going backwards 4 twice. See, when you change the direction, something peculiar happens. You see, the negative 8 is still further from the 0 than the negative 4 is. Just like over here, 8 was further to the right than the 4 was, the negative 8 is still further, and we've still gone twice. But when we insert that negative sign in, we've changed the direction we're moving on the number line. And if we move to the left on the number line, the farther to the left we get, the smaller the value of the number. So when I insert that negative sign in there, I still get further from 0. Negative 8 is further from 0 than negative 4 is, but when I change directions, further in the left is going to make it smaller. Now, that is a little bit tricky. It is a little bit weird. It is a little convoluted. I don't claim to be perfect in understanding that. However, it is very important for us to understand this idea of directionality on the number line. When we put that negative sign in there and you change the direction, the thing that was greater because it was further to the right has become less because it's further to the left. Very, very tricky, but it does explain why we have to reverse that sign. So let's look at a few examples. I'll try and make this as quick and painless as possible because most of this we already should understand. If I have 5x plus 3 is greater than negative 32, I'm still going to solve this exactly like I solved it when I was solving equations. How do I get rid of the plus 3? Subtract 3 from both sides. How do I get rid of the times 5? I either divide by 5 or multiply by 1/5, leaving us with x is greater than negative 7. That's exactly the same thing we would have done had this been an equation. The difference is instead of having a single value for my solution, I now have several values. Every number greater than negative 7 should work. Since there's an infinite number of those values, it's going to be very difficult for me to list them all. Actually, it's going to be impossible. So what I'm going to do is I'm going to illustrate it on the number line. I want all those values greater than negative 7. Well, there's negative 7. Everything to the right is bigger. But negative 7 itself is not included. The open circle reminds me to leave it out. Now, if you remember back to our first days of solving equations, we talked about how we can go back and verify that our solution is correct. We would do something like this. We would say 5x plus 3 equals negative 32, and we'd plug in the value we said would work, and we would simplify until they matched. For us, when we do inequalities, we're still going to do that, and we're going to refer to that as checking the endpoint. Notice this is greater than, but we're not checking greater than, we're checking equal to. And if we can prove that negative 7 is equal to, that's going to verify for us that this open circle is in the right spot. Now notice the circle is open, so even though we have to check this, this should not be true. This should not be true in our original equation. Negative 32 is equal to negative 32, so that is in the right spot, but the negative 7 is not a solution because we're only looking for things that are greater than. The second thing we have to do with an inequality is go back and check the direction. And we're going to do that by using the inequality itself. 5x plus 3 is greater than negative 32. And then, since we're trying to find values that are greater than negative 32, I'm going to pick any value greater than negative 7 to test. It really doesn't matter which one you picked. We've verified that the negative 7 is in the right place. The only thing we're trying to determine now is that our arrow should be pointed to the right and not to the left. So I want to pick a number greater than negative 7. In this case, I chose a negative 5. And then I simplify to see if it leaves me with something that's true. This is negative 25 plus 3, which is negative 22. Negative 22 is greater than negative 32, so I know my solutions are correct. Now, it is kind of frustrating with your inequalities because you really have four things going on here. You have the solving of the inequality, you have the graphing of the solution, you have the checking of the endpoint, and then you have the checking of the direction. It's kind of a nuisance, kind of a pain. But as you get better and better at it, it will become easier and easier. Here's another one. I want you to pause the video and try this on your own. When you restart the video, I am going to do this fairly quickly because you should already have it done. First thing I would do is do my distributive property. So property of equality says I can subtract the 160 from both sides. How do I get rid of a times 5? I multiply by 1/5, or I divide both sides by 5, leaving me with x is less than or equal to negative 3. Again, I have a number line. I want to graph all solutions. I'm looking for things that are smaller than negative 3. Those things would be to the left. In this case, notice that it is less than or equal to. The equal to means that negative 3 is a solution, so I used a colored in circle. If I did this correctly, when I do my check, I should be able to find that putting in this -3 will cause this to equal 145, or will give me a true statement. So let's plug in that -3. I simplify, the two sides are equal, and I know it works. In this case, the -3 works, and the -3 is part of our solution because equals to is part of our final answer. When I do this to check the direction of the arrow, I just need to choose anything that's on the left side of -3. I happen to choose -4. If I simplify, I get 5 times 28, and I get 140 is less than or equal to 145, which is also true. Here again, we check the endpoint, and then we check any value on the left side. Here's one more for you to try on your own. I'm going to go ahead and go with this. Again, I'm going to do it quickly because you should have already done that on your own. Let's see, I'm going to add x to both sides. I'm then going to add 21 to both sides. I'm then going to divide both sides by 5, and I get 8 is less than x. If 8 is smaller than x, that means x is greater than 8. You will find it's a lot less confusing if you get that x on the left side. Once again, we're going to graph this. Everything to the right of 8 is going to be bigger. The 8 itself is not included, so we use an open circle. To do our check, we rewrite, plug in the value that is our border. In this case, that's the 8. Verify that the two sides match one another. Then I'm going to check the inequality. In this case, I want to use things that are to the right of 8. It can be any number I want. I happen to choose 10. When you simplify, 11 is smaller than 19, and you are correct. By the way, keep in mind that when we're doing these in the video, because I have a chance to prepare these ahead of time, generally these do work out and they are correct. Keep in mind that if you do these on your own and it does not check out, that usually means you've made some kind of an error in the original problem. The whole point of doing the check is to try and spot those errors. If you don't take the time to go back and correct the errors, you've really just wasted your time by doing the check. I do want to do one more of these. -11x plus 13 is greater than -53. Again, we would solve these the exact same way. Subtract 13 from both sides, divide both sides by the -11, but notice, when I divide by that -11, I have to do something special. Just like those very first examples we did on the very first couple of slides, I had to go back and switch this sign. If you're not sure why we're doing that, you're going to need to go back and look at those first few examples again. I'm not going to talk about why we do that at this point because we should understand that. Instead, I'm simply going to remind you that anytime you multiply or divide by a negative number, you're going to have to flip that sign in order to maintain the truth of the inequality. Again, it deals with directionality on the number line. Once we go to graph that, we want things smaller than 6. In this case, 6 is left out. Rewrite, plug in that border or boundary 6, check to make sure they match, and they do. This time we're testing the directionality. We're going to pick something to the left of or smaller than the 6. I happen to choose 0. I like to choose 0. It's a lot of times easier to work with. 13 is greater than -53, and so we know we're correct on that one as well. Again, I did something very specific and very on purpose when I gave you these examples. I intentionally gave you an entire slide where the signs did not flip, where we did not multiply or divide by a negative number. And I did that on purpose because that's the way these problems tend to be. You'll do 2, 3, 4, 5, 6, 10 in a row where you don't have to concern yourself with flipping that sign because you're not multiplying or dividing by a negative. And then all of a sudden, out of nowhere, you're going to have to flip that. And if you're not being extra conscientious, you're going to forget that you were doing that. Whenever you're working with inequalities, you've got to always keep that in the back of your mind, and you've got to check for it and verify it every single time. Now, I will tell you, when you do your checks, if you forgot to flip your sign, this is a great reminder that you have forgotten that. If you get out of the habit of doing the checks, then you're kind of on your own for that. So you want to be extra careful. Once again, thank you so much for joining us. If this was useful to you, please take the time to leave us a comment in the comment section so that we know that you're out there listening. Please be sure to like and subscribe and turn on the notifications so that you can follow along with us as we are learning Algebra 1. I've gotten kind of lax in leaving you with an inspirational quote at the end, so let me go ahead and give you this. It always seems impossible until it's done. That's from Nelson Mandela from our friends over at brainyquote.com. Be sure to check them out. Thank you so much for your time. Best of luck to all of you. Take care.